Hello my friends and welcome back to the You Can Do TV channel. Restarting Bertha, the State Route 99 tunnel boring machine, marked one of the most complex TBM recovery operations ever undertaken. After extensive investigation, Seattle Tunnel Partners confirmed that damage to the outer main seals required a full retrieval of the machine's cutterhead and drive assembly. In March 2015, nearly 2,000 tons of TBM components were lifted to the surface through a specially designed and constructed access shaft, an unprecedented engineering effort. Working closely with TBM manufacturer Hitachi Zosen, the team installed a newly designed bearing block, outer seal ring, and an upgraded seal system that allows improved access for future inspection and maintenance. Additional repairs included replacement of the center pipe, damaged pinions on the cutter drive motors, and reinforcement of the TBM structure with added steel plates. The cutterhead tool configuration was also optimized to improve excavation efficiency for the remaining tunnel drive. By August 2015, the repaired cutterhead and drive unit were carefully lowered back underground. Crews reconnected thousands of cables, hoses, and hydraulic lines, followed by extensive structural welding to restore the front shield. Precision measurements, no-load testing, and load testing were conducted to verify tolerances, clearances, and system performance. Once backfilled and groundwater controls were gradually deactivated, Bertha resumed tunneling under closely monitored conditions, advancing cautiously towards stabilized ground before returning to full excavation operations. High in the Swiss Alps, beneath rock, ice, and centuries of geological pressure, the Rhythm Pumped Storage Plant project unfolded as one of the most demanding tunneling operations ever undertaken. This is a story of extreme conditions, engineering perseverance, and innovation deep inside the mountain. In May 2019, work began not underground, but at the surface of Lago Rhythm. Before large-scale excavation could proceed, a compact and highly efficient construction water purification plant had to be installed at the lake's retaining wall. Because of the remote alpine location, the entire system was flown in by helicopter. Small in size, yet technologically advanced, the plant was designed to treat water from the tunnel construction site with exceptional efficiency, demonstrating how modern infrastructure projects can align with environmental protection. Early exploratory drilling revealed severe geological challenges. Down to depths of around 200 meters, the rock mass was heavily fractured, porous, and water-bearing. These conditions made conventional tunneling extremely risky. To mitigate this, engineers decided to first drive a deep access gallery into more competent rock. Only from this depth would the steep pressure shaft rise toward the lake. After about 400 meters of advance, expectations of drier rock proved wrong. A blast triggered a sudden inflow of water under pressures of up to 10 bars, equivalent to a 100-meter water column. Driving forward was no longer safe. Exploratory drilling revealed water inflows of up to 100 liters per second, confirming that the rock mass was far more fractured than predicted. The sloped shaft, approximately 400 meters long with a diameter of 3.2 meters, was designed with an inflection point and two different gradients, reaching slopes of up to 45 degrees. Excavating such a shaft required a purpose-built solution. A custom tunnel boring machine, TBM, was developed specifically for this project, capable of operating under extreme gradients and in highly variable rock. Construction began in January 2019 with drill and blast excavation of the lower pressure gallery. Each blast was followed by mechanical scaling, profile shaping, and immediate support using shotcrete and steel ribs where required. Ice-cold alpine water continuously entered the tunnel, creating harsh working conditions. More than 250 blasting rounds and over 20,000 drill holes were planned, pushing both physical endurance and technical precision to the limit. To stabilize the situation, the final section of the tunnel was sealed with a concrete plug, and an innovative injection shield system was introduced. Alternating sequences of drilling, sealing, and excavation were used. A hybrid injection method combined conventional cement grout with a high-viscosity synthetic resin. Cement was effective in fine fractures, while resin prevented washout in large, water-bearing fissures. Over 14 injection shields and nearly 1,000 injection boreholes, this approach successfully sealed the aquiferous zone, an achievement that surprised even seasoned experts. Only in February 2021, nearly a year behind schedule, could construction of the shaft-based cavern begin. This marked the transition to full TBM operations. The launch ramp guided the machine into the shaft at an initial slope of 26 degrees. Delivered in 6 major components, the TBM was assembled underground, reaching a total length of nearly 100 meters. Once operational, the machine advanced in strokes of 1.2 meters. Its 23 roller cutters fractured the rock under pressures of up to 500 tons, while a gripper shield braced against the tunnel walls. Excavated material slid downward through gravity-assisted chutes, aided by water from controlled inflows. A complex system of trailing units supplied power, ventilation, hydraulics, shotcrete, and material transport. Progress was steady, but never routine. After 4 months, the TBM had advanced 450 meters vertically and gained 200 meters in elevation. Logistics remained extremely complex. All materials passed through a 38-meter deep access shaft, coordinated via cableways and tunnel rail systems, with virtually no storage space on the machine itself. In total, more than 85 meters of liner plating and over 200 tons of steel and concrete were installed across multiple fault zones. In one particularly critical area, Shotcrete was injected directly through the cutterhead to stabilize a cavity, a risky but ultimately successful maneuver that saved weeks of work. Despite all obstacles, the TBM continued upward, navigating the inflection point and reaching slopes of 42 degrees held in place by its grippers alone. Cutter replacements, each weighing around 80 kilograms, were performed manually in confined spaces. By the end, the machine had excavated more than 10,000 cubic meters of rock. The TBM was dismantled in the slide chamber and transported out. The remaining tunnels were finished by conventional methods, completing the underground system of the new pumped storage plant. While much work remained before water would flow to the turbines, the tunneling phase stood as a landmark achievement. The Rhythm project is ultimately a testament to expert crews, adaptive engineering, and the ability to confront uncertainty deep beneath the earth. Under extreme conditions, innovation and experience turned geological adversity into lasting infrastructure, powering the future from the heart of the mountain. Between 2009 and 2018, Axpo implemented the Limmer pumped storage power plant expansion, a large-scale underground hydropower project located in the Swiss Alps. The facility exploits a vertical head difference of approximately 630 meters between Lake Mutt and the Limmer Reservoir to provide a total installed pump turbine capacity of 1,000 megawatts, significantly enhancing grid balancing and peak load capability. Excavated material was conveyed through an underground haulage system to a crushing facility. A significant portion of the processed rock was reused for dam construction at Lake Mutt, while remaining aggregates supplied an underground concrete batching plant. This plant produced structural concrete for cavern linings, foundations, and reinforcement works. In total, more than 80,000 cubic meters of concrete were placed within the underground structures. Parallel to tunnel excavation, the powerhouse and transformer caverns were developed using staged, top-down excavation methods. The main powerhouse cavern, with dimensions of roughly 150 meters in length and 50 meters in height, was excavated entirely from solid rock. Controlled drilling and blasting techniques were predominantly applied, followed by systematic rock support and stabilization. Once cavern excavation was completed, installation of hydraulic and mechanical systems began. Draft tubes for the pump turbines were positioned first, followed by concreting of turbine foundations and powerhouse linings. The cavern geometry was transformed into a closed, load-bearing arch system capable of withstanding long-term rock pressure. Electrical grid integration required routing high-voltage cables through the access tunnel to the tier-fed substation. A new 380 kilovolts overhead transmission line extending 17 kilometers was constructed as part of the Swiss extra high-voltage network. The line includes 53 pylons, some exceeding 89 meters in height, installed using helicopter-assisted lifting due to difficult terrain. Transportation and installation of major components presented further engineering challenges. Individual elements, such as spiral casings and transformers, weighed up to 190 tons. The access tunnel and a specially designed funicular system with a 200-ton load capacity enabled direct delivery of these components into the powerhouse cavern. Assembly of the machine groups involved embedding the spiral casings in reinforced concrete, installing pump turbine runners, thrust bearings, generator stators, and rotors. Each generator rotor weighed approximately 330 tons and was assembled in situ. By November 2015, the first units were synchronized with the power grid. The hydraulic system includes inclined pressure shafts excavated at 40 degrees, upstream and downstream pressure tunnels, penstocks totaling approximately 2 kilometers in length, and optimized intake and outlet structures designed for flow rates up to 200 cubic meters per second. Completed in stages between 2015 and 2018, the Limmer Pump Storage Power Plant represents a benchmark in underground hydropower engineering, delivering high operational flexibility, rapid mode switching, and long-term grid stability. The Jammu-Udhampur section of National Highway 1A is a critical transportation corridor linking India's northern frontier in Jammu and Kashmir with the rest of the country. The route carries approximately 15,000 vehicles per day, including nearly 3,000 defense vehicles, in addition to heavy civilian and tourist traffic bound for destinations such as Vaishno Devi, Amarnath, and Srinagar. Improving this corridor was therefore not only a transportation upgrade but a strategic infrastructure requirement. The project involves four-laning a 65-kilometer stretch through highly challenging Himalayan terrain. The objective was to significantly improve alignment geometry, reduce sharp curves, and enhance safety while maintaining traffic flow during construction. Once completed, travel time between Jammu and Udhampur is expected to be reduced from nearly 2 hours to approximately 45 minutes. Road construction in mountainous terrain presents complexities far beyond conventional highway projects. The scope included extensive hill cutting, multiple tunnels, numerous bridges across deep valleys, and large-scale slope stabilization works. To meet an accelerated schedule of 36 months, the engineering team adopted a strategy focused on innovation, standardization, and parallel execution. A key structural innovation was the standardization of bridge spans across the alignment. This enabled large-scale precasting of superstructure elements in dedicated casting yards. Precast girders and deck segments were manufactured simultaneously with foundation and substructure works on site, significantly reducing construction time and minimizing dependence on weather conditions. Tunneling operations required further innovation due to variable rock strata and environmental constraints, including proximity to wildlife sanctuaries where realignment was not feasible. In addition to conventional drilling and blasting, mechanical excavation methods were introduced. Air-cat drum cutters were deployed to achieve precise rock cutting with reduced vibration, while road headers were used in medium to hard rock formations to accelerate tunnel advance rates. Tunnel support systems also departed from conventional practice. Instead of a full cast-in-situ concrete lining applied after excavation, the project utilized steel fiber reinforced shotcrete, SFRS. During excavation, 2 layers of SFRS combined with lattice girders provided immediate ground support. A final shotcrete layer was applied after breakthrough. This approach eliminated the need for heavy gantry formwork and substantially shortened the tunnel construction cycle. One of the most complex alignment challenges involved a steep hillside with a river valley on one side. Design requirements specified a minimum operating speed of 60 kilometers per hour, ruling out hairpin curves. Engineers executed large-scale earthworks, cutting the hill by nearly 40 meters while simultaneously raising the valley side by approximately 50 meters using engineered embankments. The result was a smooth horizontal loop, allowing safe, high-speed vehicle movement. The young and geologically diverse Himalayan rock formations required multiple retaining solutions. Depending on site conditions, reinforced concrete retaining walls, gabion walls, and anchored reinforced earth (AR) walls were employed. Continuous geological reassessment was necessary, as hard rock layers often transitioned abruptly into soft soil zones. Throughout construction, traffic management was maintained to ensure at least 2 operational lanes remained open. Nearly 8,000 workers and a large fleet of specialized machinery operated in coordinated shifts, supported by incentive-based productivity programs. The Jammu Udhampur Highway project demonstrates how advanced engineering methods, adaptive design, and disciplined execution can deliver complex mountain infrastructure ahead of schedule while meeting strategic, environmental, and social requirements. The bridge to Russky Island in Vladivostok stands as one of the most ambitious cable-stayed bridge projects ever undertaken, combining record-setting span length with innovative construction strategies to meet both structural performance and climatic challenges. From a structural standpoint, the bridge features a central cable-stayed span of 104 meters, making it the longest cable-stayed span in the world at the time of commissioning, with a total crossing length including approaches of 100 meters. 2 towering A-shaped reinforced concrete pylons, each rising approximately 320 meters above ground, support the deck through a system of 168 parallel strand stay cables. The site conditions imposed substantial engineering constraints. The narrow strait reaches depths of up to 50 meters, while the region experiences extreme temperature fluctuations, wind speeds exceeding 36 meters per second, and significant ice loads during winter months. These environmental demands informed both materials selection and structural design, requiring robust corrosion protection for stay cables and an aerodynamically optimized deck cross-section capable of withstanding dynamic wind loads. Foundations were established through deep piling systems on both the mainland and island sides. On the Vladivostok side, reinforced concrete piles were driven to depths of around 77 meters below ground, with approximately 120 auger piles installed beneath each pylon to distribute the weight of the towers and central span into competent strata. Pylon construction employed self-climbing formwork systems to achieve high-quality cast-in-situ reinforced concrete towers while accelerating cycle times. These systems allowed seamless progression of concrete pours up to 320 meters height, overcoming the challenges of an A-shaped geometry that precluded standard formwork solutions. Concurrently, installation of the stay cables commenced even as the pylons were still being cast, reducing overall project duration. The superstructure design incorporated an orthotropic steel box girder for the central span, paired with pre-stressed concrete sections on side spans and viaduct approaches. Steel panels were prefabricated and delivered by barge to the construction site, with precision lifting operations positioning them at heights of up to 76 meters above water level. Welded field connections and high-strength bolted joints ensured structural continuity and facilitated rapid assembly. Stay cable technology was central to the structural performance of the bridge. Manufactured and installed by specialist contractors, the parallel strand stay cables comprised bundles of galvanized steel strands encased in high-density polyethylene housings to provide corrosion resistance and ultraviolet protection. Cable lengths ranged from approximately 136 meters to nearly 580 meters, depending on their position along the span. Tight geometric tolerances were maintained through advanced survey and alignment procedures during erection. Aerodynamic shape optimization of the deck cross-section was achieved through wind tunnel testing of scale models during detailed design, ensuring adequate stability under gust and storm conditions characteristic of the Sea of Japan environment. The integration of deep foundations, high-performance concrete towers, orthotropic steel deck structures, and long-reach cable systems enabled the Russky Bridge to meet its structural and climatic requirements. Construction logistics also incorporated marine transport, on-site fabrication yards at both ends of the span, and coordinated lifts for large modular elements, demonstrating advanced project planning and execution techniques. Officially opened in July 2012, the bridge not only provided a reliable high-capacity connection between Vladivostok and Russky Island, but also exemplified cutting-edge cable-stayed bridge engineering under extreme environmental conditions. Amid the steady rhythm of heavy lifting and precise coordination, the girder erection works on the Solo-Yogyakarta Toll Road advance into a critical construction phase. At West Bridge 2, this operation represents a key step in shaping the elevated structures that will define the corridor's final alignment. The works are executed by PT Adi Prasada Beton as part of a multi-bridge erection program extending up to STA 13. At this stage, erection activities are underway on the 7th bridge out of approximately 17 planned structures along this section. Each girder installation follows a controlled and methodical sequence, governed by approved method statements, structural specifications, and site-specific safety procedures. Precast concrete girders are delivered to the site and positioned on prepared working platforms. Prior to lifting, all cranes, rigging systems, and lifting accessories are inspected to confirm capacity, mechanical condition, and compliance with safety requirements. Lifting operations are conducted under a single command system, ensuring clear communication and synchronized movement throughout the process. Once hoisted, girders are carefully aligned using survey controls and reference markers to achieve the required geometry and bearing tolerances. Quality inspections verify concrete integrity, dimensional accuracy, and surface condition before final placement is approved. Environmental and site constraints, including weather-related challenges, are managed through adaptive planning and platform preparation. Safety control focuses on equipment readiness, ground stability, and team coordination, allowing erection works to proceed efficiently without compromising operational discipline. Through structured execution, technical precision, and coordinated teamwork, the girder erection process contributes steadily to the timely realization of the Solo Yogyakarta toll road infrastructure. Concrete is one of the most widely used construction materials worldwide due to its high compressive strength, durability, and versatility in structural applications. Production begins at the batching plant, where cement, aggregates, water, and admixtures are proportioned through a controlled dosing process based on an approved mix design. The materials are then thoroughly mixed to achieve uniform consistency and defined fresh concrete properties. Before dispatch, mixer trucks pass through quality control laboratories, where both raw materials and finished concrete are tested in accordance with international ASTM standards. The concrete is transported to the construction site in rotating mixer trucks to maintain homogeneity and delay initial setting. Upon arrival at the site, the concrete must be verified prior to discharge by checking delivery documentation, including mix type, volume, specified strength, slump, loading time, and truck identification. Concrete placement must be carried out using methods that prevent segregation and excessive freefall. The addition of water on site is strictly prohibited, as it reduces strength and increases the risk of cracking. After placement, the concrete is consolidated by mechanical vibration to eliminate air voids and ensure proper particle arrangement. Curing is a critical final stage, aimed at maintaining adequate moisture and temperature conditions to support cement hydration. Proper curing improves strength development, minimizes cracking, and enhances long-term durability, and should be maintained continuously for a minimum of 7 days. The PowerScreen DX India manufacturing facility in Hosur is a high-precision production center dedicated to the fabrication and assembly of mobile crushing and screening equipment for international markets. Production starts in the fabrication shop, where CNC-controlled cutting machines, press brakes, and precision welding stations are used to manufacture structural components such as mainframes, hoppers, and support structures. These components are engineered to withstand high dynamic and impact loads, typical of crushing and screening operations. Dimensional accuracy and weld quality are continuously verified through in-process inspections. Quality assurance begins upstream at supplier facilities, where materials are evaluated under Terex-approved process controls. Upon arrival, components undergo shot blasting and dual-layer protective coating, providing corrosion resistance that meets international durability requirements. Assembly is carried out on a multi-model flow-line manufacturing system, enabling efficient production of different machine variants while maintaining strict process discipline. Precision measurement tools are used to ensure accurate installation of power units, hydraulic circuits, electrical systems, conveyors, and screening modules. Each subsystem is individually tested before final integration. Completed machines are subjected to functional testing on dedicated test benches, followed by comprehensive final inspection and pre-delivery validation to confirm performance, safety compliance, and operational reliability. Permanent Shotcrete stabilization using Titan micropiles is an effective solution for slope stabilization and soil nailing applications in accordance with national technical approval. Installation is carried out using a compact drilling rig connected to a pressure grouting plant. The hollow steel bar functions simultaneously as drilling rod and reinforcement. Rotary percussive drilling is performed while injecting drilling or flushing fluid, ensuring borehole stability. The rod is extended using threaded couplers until the design depth is reached. The process then transitions to dynamic pressure grouting with grout suspension. After curing, shotcrete facing is applied, allowing excavation support to be constructed progressively and safely. Permanent pavement repair using gap mastic and gap patch provides a durable, all-weather solution for restoring asphalt surfaces affected by structural distress, surface wear, and localized failures. Designed for long-term performance, these polymer-modified materials bond directly to existing pavement, creating a seamless, waterproof repair that resists traffic loads and environmental exposure. Shoulder repair in Nebraska. Gap mastic is applied along pavement edges where erosion and settlement have compromised support. The material is poured or squeegeed into place, forming a flexible yet strong edge reinforcement that prevents further edge cracking and moisture intrusion. In depression repairs, damaged areas are cleaned, dried if necessary, and filled with gap patch to restore proper surface profile and ride quality without the need for milling or full-depth reconstruction. Wide crack repair is one of the most effective applications of gap mastic. Cracks wider than conventional sealant limits are routed or cleaned, then filled flush with the pavement surface. The mastic bridges the crack, accommodating movement while preventing water infiltration that leads to base failure. For drain repairs in Utah, gap materials are used to seal joints, voids, and interface areas around drainage structures, ensuring proper water flow while protecting surrounding asphalt from washout. In Minnesota, pothole repairs are completed quickly by removing loose material and filling the cavity with gap patch, which cures rapidly and withstands freeze-thaw cycles. Raveling repair involves surface preparation followed by a thin application of gap mastic to lock in loose aggregate, restore surface integrity, and extend pavement life. Overall, gap mastic and gap patch enable permanent, cost-effective pavement repairs with minimal traffic disruption, delivering enhanced durability, flexibility, and resistance to moisture-related damage across a wide range of roadway conditions. The longest HDD crossing in Malaysia was undertaken to replace an aging sub-seawater main supplying potable water between Pulau Indah and Pulau Ketam. The original pipeline, installed in 1992 using conventional submarine dredging, suffered repeated leakages and structural damage due to shallow burial and exposure to marine activities, resulting in frequent service disruptions and significant water losses. A feasibility assessment identified horizontal directional drilling, HDD, as the most suitable long-term solution. Compared with open-cut dredging, HDD reduced construction costs by approximately 33% and minimized seabed disturbance, requiring less than 1,000 cubic meters of soil excavation versus hundreds of thousands using conventional methods. The new steel pipeline, with an outer diameter of 406 millimeters, was installed at a minimum depth of 16 meters below the seabed, providing enhanced protection and long-term reliability. The HDD installation followed 4 key stages: installation of a conductor casing, pilot hole drilling, multi-stage reaming to a final diameter of 762 millimeters, and controlled pipe pullback. A high-capacity HDD rig capable of handling long-distance crossings was deployed, supported by drilling barges and marine logistics. All welded joints underwent non-destructive testing, hydrostatic pressure testing, and coating inspection prior to installation. Completed in March 2015, the HDD crossing delivered a durable, environmentally responsible solution, while setting a national benchmark for long-distance subsea pipeline installation. The girder setting operation for the Cypress Gardens Emergency Bridge Replacement, S8-9, on July 31, 2014, represents a critical phase in restoring structural continuity to the crossing. Following foundation and substructure completion, precast concrete girders were delivered to the site and staged for installation. Heavy-lift crawler cranes were positioned with carefully engineered lift plans, accounting for girder weight, radius, and site constraints. Each girder was rigged using certified lifting hardware and raised in a controlled manner to minimize rotation and dynamic loading. During placement, crews coordinated crane movements with spotters to align the girders precisely onto bearing pads atop the piers and abutments. Tolerances for elevation, spacing, and lateral alignment were verified immediately to ensure proper load transfer and future deck geometry. Temporary bracing was installed as required to maintain stability until all girders were set. This rapid, methodical girder installation was essential to the accelerated schedule of the emergency replacement, enabling subsequent deck forming, reinforcement, and concrete placement to proceed without delay while meeting structural and safety requirements. This operation documents the placement of a single-span segment of the elevated light rail transit structure in Calgary using a launching truss system. The launching truss is positioned longitudinally along the alignment, allowing precast concrete girder segments to be transported, lifted, and accurately set without ground-based lifting equipment. Each segment is hoisted into position, aligned to survey controls, and temporarily supported by the truss while final bearing placement and connections are completed. This method minimizes disruption at ground level, improves installation accuracy, and enhances safety in constrained urban corridors where access and lifting space are limited. The asfalto-borracha wet process is an advanced pavement technology in which crumb rubber derived from recycled tires is blended directly with hot bitumen, allowing the rubber to react and swell before the binder is mixed with mineral aggregates. During construction, a lead truck moves ahead of the paving operation to distribute the prepared rubber material in a controlled manner, ensuring uniform coverage. A dedicated asphalt paver then places the asphalt-rubber mixture, precisely controlling layer thickness, surface evenness, and laying temperature. Immediately after paving, vibratory and pneumatic tire rollers perform systematic compaction. The result is a pavement with enhanced flexibility, superior crack resistance, reduced noise, and extended service life. The Vogele Super 1900-3 asphalt paver operates as a high-precision machine designed for large-scale road construction and rehabilitation projects. Powered by a fuel-efficient diesel engine, it is equipped with the Erga Plus 3 operating system, allowing precise control of paving parameters. Asphalt mix is transferred smoothly from the hopper to the augers, where it is evenly distributed across the full paving width. The advanced screed system maintains consistent layer thickness, accurate crossfall, and a uniform surface texture. Automatic grade and slope control systems ensure compliance with design elevations and profiles. With a paving width of up to 11 meters and high material throughput, the Super 1900-3 delivers stable operation, excellent mat quality, and optimal conditions for subsequent compaction, resulting in durable and smooth asphalt pavement. The NKR Demolition Extreme Super Machine, configured with a 50-meter long reach boom, stands at the forefront of modern chimney demolition technology. Designed for precision and control, this powerful machine allows tall industrial chimneys to be dismantled safely from the top down, eliminating the risks associated with blasting or manual demolition at height. The long-reach boom is manufactured from high-strength, fine-grained structural steel, optimized to reduce deflection while carrying demolition attachments weighing up to 3 to 5 tons at height. Hydraulic power is supplied by a high-capacity system delivering over 600 to 700 bars working pressure, ensuring consistent performance for concrete crushers, steel shears, or pulverizers. Advanced operator assistance systems, including load moment control, boom angle monitoring, and real-time stability indicators, enhance operational safety. Combined with precise hydraulic control and proven attachment technology, this super machine enables NKR Demolition Group to execute chimney demolition in a controlled, efficient, and fully engineered manner, setting new benchmarks in extreme long-reach demolition. The heavy haul operation by J. Super & Son in Canton, Connecticut, showcased the precision and engineering required to transport an oversized turbine and generator assembly. The convoy carried an exceptionally heavy load, demanding a carefully engineered route and specialized equipment to ensure safe passage through the town's challenging terrain. One of the most complex aspects was crossing a section of roadway where a stream runs diagonally beneath the existing bridge. To accommodate the turbine's extreme weight, crews installed a temporary modular bridge directly over the original structure. This solution redistributed load forces, protecting both the convoy and the underlying bridge. As the transport progresses, you can clearly see the left side railing of the original bridge, indicating the offset and the diagonal water flow below, conditions that required exact alignment and precise engineering calculations. Self-propelled modular transporters equipped with hydraulic suspension supported the turbine, allowing operators to adjust height and maintain stability over uneven ground. Escort teams monitored clearances, structural behavior, and traffic control throughout the move. This operation highlights the coordination of civil engineering, heavy haul logistics, and road safety management, demonstrating how oversized industrial equipment can be transported safely, even in constrained rural environments. The transport of wind turbine blades requires specialized equipment, and the Coriolis KTB 1000 is designed specifically for this purpose. With a dead weight of 35,000 kg and adjustable counterweights ranging from 3,000 to 50,000 kg, the system manages extreme loads with precision. Its load moment capacity of 350 metric tons ensures stability when handling long turbine blades. The KTB 1000 features advanced articulation, including a tilt angle of 60 degrees, pitch capability of 360 degrees, and a pivoting angle of 15 degrees, allowing operators to maneuver blades safely through tight turns, varying terrain, and steep slopes. When operating on inclines, if the wind direction is 45 degrees below horizontal, the device pitches 45 degrees to maintain balance. On upward slopes, the system adjusts pitch to counteract wind forces, preventing the blade from lifting. This combination of mechanical precision, adjustable counterweights, and real-time pitch control ensures safe and efficient transport of massive wind turbine blades, even in challenging environments. Handling oversized load trucks through a roundabout requires precise planning, expert driving, and specialized equipment. As the convoy approaches the circular junction, escort teams coordinate traffic control, ensuring the roadway is clear for the extended vehicle combination. The truck, often equipped with a multi-axle lowboy or modular trailer, enters the roundabout at extremely low speed to maintain stability and avoid trailer swing. Because of the load's width and length, the driver intentionally overrides lane markings, using the entire roundabout, including the truck apron, while pilot cars guide the maneuver. Hydraulic steering on the rear axles allows the trailer to pivot smoothly, preventing contact with curbs, signs, and center islands. This controlled navigation demonstrates the precision required to move heavy industrial components safely through complex, confined road infrastructure. On November 4, 2015, the convoy Exceptionnel Boudagaz passed through the Rond-Point d'Argent-sur-Sauldre, marking a remarkable display of heavy-haul logistics in France. The convoy consisted of 3 specialized trucks, each transporting a massive liquefied gas tank for Boudagaz in Aubigné-sur-Nère. Each vehicle, fully loaded, weighed approximately 330 tons, measured 65 meters in length, and reached 8 meters in height, requiring meticulous planning to navigate public roads safely. Due to the extreme dimensions and weight of the loads, the convoy traveled at a controlled speed of around 10 kilometers per hour, allowing drivers and escort teams to maintain full operational control and ensure the safety of surrounding traffic. Special attention was paid to the route, with engineers assessing clearances, bridge capacities, and turning radii at intersections and roundabouts. The Rond-Point d'Argent-sur-Sauldre, a critical point along the route, demanded precise maneuvering, highlighting the skill and coordination of both drivers and support teams. Each truck was equipped with reinforced trailers and hydraulic steering systems, allowing for the careful negotiation of curves and gradients. Escort vehicles accompanied the convoy to manage traffic, communicate with authorities, and monitor load stability. Communication between the convoy team, local authorities, and traffic controllers was continuous, ensuring any unexpected obstacle could be addressed immediately. This operation exemplifies the complexity of moving oversized industrial equipment over public infrastructure. From route planning to vehicle engineering, and from speed regulation to real-time coordination, the passage of the Convoy Exceptionnel Boutagaz demonstrates the combination of advanced logistics, engineering expertise, and operational precision required to transport massive industrial cargo safely and efficiently across regional roads in France.